Alright, so in the previous class I had stated this Cauchy Schwartz inequality and then shown that if u is 0, so we had shown that if u is 0, so as a proof we have shown that if u is 0 then a star holds. Alright. So to complete the proof, let us assume that u is not the 0 vector. So assume now, so assume u is not the 0 vector, fine. So I can divide by length of u, that is one way, and we can try to prove it by some manipulation. I will not get into that part, fine. What we will do is that we will try to prove it only for the case when I have scalars are real numbers, alright. So let us try to see in terms of real numbers where does we get these ideas, alright. You can prove it for complex, some manipulation is required, but for real everything is nice. So let us try to understand that. What we have is, look at this vector u minus alpha v, alright. Let us look at this. We have assumed that u is non-zero. I want to look at length of this square. Now what we know is that this vector u minus alpha v is either a 0 vector or non-zero vector, but this scalar quantity square, the length of something is always greater than or equal to 0, alright. So we already know that the square of this is greater than or equal to 0, fine. Now let us write it back in terms of inner product. So we can write it as u minus alpha v, u minus alpha v. Important, we are assuming that alpha belongs to R, alright. We are looking at only real scalars. Therefore I am able to do this manipulation, otherwise something extra has to be done. So I can write it as u comma u minus alpha v minus alpha v times u minus alpha v. I am writing this expansion here taking time, but later on I will just go very fast. I may do mistakes, but it will be your responsibility to make corrections in those expressions, alright. But here I am doing it nicely. So what we know is that since I am looking at over R, so xy is same as yx, alright. I do not have bar coming into play, is that okay? So since there is no bar, I can write it as uu minus u comma alpha v, sorry, plus this minus alpha times vu, so alpha times, so let me again, I think there may be confusion. So let me write it as alpha v u minus minus plus alpha v comma alpha v, so which is same as norm of u square plus, since as I said inner product of xy is same as inner product of yx, fine. So I can write this as minus alpha times uv, this is also minus alpha times uv itself, vu, so let me write vu plus alpha square vv, which is same as norm of u square minus 2 alpha inner product of uv plus alpha square norm of v square, alright, fine. Is that okay? So I can write this. Now what I know is that, look at this expression. This expression, if I look at this expression, alright, the last part says that this, the last part, the last expression is valid for all values of alpha, alright. So what we are saying is that I have something in alpha which is always non-negative. What does it mean? If I am saying that something is non-negative and alpha, if I look at this expression, we are looking at alpha square norm of v square minus 2 alpha uv plus this is greater than or equal to 0 for all alpha. It is quadratic in alpha, alright, it is quadratic in alpha, fine. So if I assume that v is not 0, so I should have taken v to be non-zero in place of u, alright. So that is a small mistake that I have done, but anyway, so I could have started here with v to be 0, got the result, then assume v is non-zero and then proceeded here. So assuming that norm of v is not 0, so norm of v is not equal to 0, will give me that this expression is quadratic in alpha and it is non-negative for every alpha. Now when I say that some quadratic is not 0 is positive or greater than equal to 0 for every alpha, it means that the discriminant, alright, the discriminant, that is b square minus 4ac, discriminant of the quadratic, alright, should be greater than equal to 0 or less than equal to 0. What should it be? Fine. So since I am saying that this is non-negative, it means that the curve is always above the x-axis, or it may touch the x-axis at some point, fine, but it is always above. It means that I don't have anything below. It means that I don't have any real roots. If there is a real root, it is exactly 1, it is repeated twice, fine. So the discriminant has to be less than equal to 0. So this has to be less than equal to 0. So let us look at this part. B square is 4 times uv whole square. Whole square is same as writing like this, b square minus 4 times, so I wrote it opposite, so b square minus 4 ca I wrote here. This has to be less than equal to 0. This 4 cancels out. This implies uv this square is less than equal to norm of u square into norm of v square, and therefore I get that uv is less than equal to this, fine. And this is what we wanted. The Cauchy Schwartz inequality is, this is what it is, that the length of uv, alright, the vector absolute value of this uv is less than equal to this. So let us recall, let us see that part. So this is what we have, alright, fine. So it just follows, for the real case, it directly follows from the idea of quadratic, that if the quadratic is always non-negative, then the discriminant has to be less than equal to 0, and we are done, fine. What is more important is that when will this be equality, fine. So there is a equality here. If there is a equality here, it means that there has to be a equality here. Now equality here means that the discriminant is 0. Discriminant is 0 means, what does the discriminant means 0? The vector has to be 0 in the sense that there is only one solution for u, alright. So it means that this has to be 0, fine. I am saying that this expression is same as this expression. Now we are saying that there is only one root, and what is that root? There is a particular choice of alpha for which u equal to alpha v, alright. So equality implies, equality here will imply that this part is 0, so there is only one root for alpha. If there is only one root for alpha, it means that there is a choice of alpha for which this is 0, fine. So since there is a choice for alpha, this is 0, so there is a equality implies there exists a choice for alpha, such that norm of u square minus 2 alpha this plus alpha square times norm of v square is 0 for this particular choice of alpha, whatever that alpha is. So this will imply that norm of u minus alpha v square is 0 for the same choice of alpha, alright. For this same choice of alpha, this is 0, and this implies that u is equal to alpha v, because the norm of something is 0 means the vector is 0. Is that okay? Fine. So this is a very important thing for us. You need to understand this. With slight modification, you can prove it for the complex. Be careful, but it will not be the idea of discriminant, because we don't have any complex number. We will have to use some idea, what is called, we will have to write alpha as, I don't know, I have written here in terms of the other way around. So you may have to define alpha is equal to something uv bar divided by norm of u and things like that, something you have to do. So just try it out or look at the notes and things like that, fine. So there is a small modification that you need to do. Let us look at the use of this, application. Alright. So let a and b be two real numbers which are positive, fine. They are positive numbers. We can talk in terms of, so we know what is called a arithmetic geometric progression. So AP is greater than equal to GP, fine. Can you use these ideas? So let us try to prove this. AP is greater than equal to GP, fine. So I have assumed that A and B are positive, fine. Since A and B are positive, so I can define my vector x as u as a square root of A, a square root of B, v as a square root of B, a square root of A. So when I look at the inner product, the standard inner product, which is uv inner product is nothing but v transpose u, it will be a square root of B, a square root of A times a square root of A, a square root of B, which will be equal to 2 times a square root of AB. So I get the expression corresponding to GP, fine, alright. So I think it should be not AP GP but AM GM, alright again. So AM GM inequality, fine. So I got this. And what about the length of U? Length of U is same as length of V, which is same as, if you look at, A square root of A square plus a square root of B whole square, a square root, which is same as a square root of AB, fine. So therefore when I look at norm of U into norm of V, I get a square root of AB, sorry, the square root of A plus B, and so it is a square root of A plus B into the square root of A plus B, which is A plus B, alright. So therefore this, when I say is less than equal to norm of U into norm of V, what we get here is that 2 times a square root of AB is less than equal to A plus B, which is what AMGM inequality is. AMGM inequality says this is less than equal to A plus B upon 2, alright. So we have proved the AMGM inequality, fine. So this is what you have to look at. Another example that I would like you to see here is a slight change in this too. Take U as it is a square root of A, a square root of B. Take V as 1 upon a square root of A, 1 upon a square root of B. You take U and V as different, fine. There is a small difference. Therefore, if I look at UV, which is same as UV here, so UV, so V transpose U will be equal to 1 upon root A, 1 upon root B times root A, root B. This will be equal to this into this, cancels out, you get 1, 1. So 1 plus 1, which is 2, fine. But if I look at norm of U is, alright, A plus B, a square root. Norm of V is equal to 1 upon A plus 1 upon B, a square root. So therefore what I see from here is, if I want to write here UV, which is 2, I hope I have done correctly, this is equal to less than equal to norm of U into norm of V, which is a square root of A plus B into a square root of 1 upon A plus 1 upon B, and therefore I get here is that A plus B into 1 upon A plus 1 upon B is greater than equal to 4, alright. So I get this inequality, and this can be generalized for any n. So I would like you to try that out, that in place of looking at A and B, just look at x1, x2, xn to be greater than equal to 0, fine. Then you will have here x1 plus x2, so you will get here summation xi here, you will get summation 1 upon xi here, and this should be greater than equal to what, fine. So just look at the idea here, since you are looking at this, it will be 1 plus 1 plus 1 n times, so will it be n square, that is the question, alright. So try that out yourself, fine. Third one that we are going to look at is, suppose you have got U as U1, U2, Un, V as V1, V2, Vn. Again let us look at the standard inner product, we are looking at over Rn itself. So UV is equal to V transpose U, which will be nothing but U1 V1 plus U2 V2 plus Un Vn, and therefore this part is less than equal to this into this, implies that, so implies that summation I going from 1 to n Ui Vi, this mod is less than equal to summation Ui a square root because of this U, and again a square root of summation I going from 1 to n vi square. All right, fine. So I can do such a thing, and this is what we required when we looked at C2 or R2 or R3. That, so look at this part, in place of R3, it just corresponds to looking at U1 V1 plus U2 V2 plus U3 V3 plus U3 V3 upon, look at these two, U1 square plus U2 square plus U3 square, the square root, into a square root of V1 square plus V2 square plus V3 square is less than equal to 1, and this absolute value tells me that this is also this. Fine. So this is the one that we had in our school. Fine, we assumed it and defined the cos theta. Fine. So we have been able to do things. So in general, so let's go back to the general setup. So I had enough examples here you would like to look at. There are some examples in assignments also, so you need to understand and try them out. Fine. Now, so application of this as another thing is that, seen that length of absolute value of this is less than equal to this. Fine. Therefore, can define cos theta as this divided by this. Now, somebody can ask that why are you defining it as cos theta, why not as sin theta and things like that, why not cos 2 theta. I would like you to understand them, go to properties of triangles and see that we need to define it as cos theta, there is no other choice. This part tells me that -1 is less than equal to uv divided by this, that's all it says, but why it has to be cos theta, that one has to understand. Fine. So we define this cos theta as this, you can compute angles and so on. For us what is more important is, we say, so definition, u and v are said to be orthogonal if inner product of u with v is 0. Is that okay? Now whether it is a real inner product of space or complex, whatever it is, we say that they are orthogonal if the inner product between them is 0. Is that okay? That's important for us. So example, in R2 the vector E1 is orthogonal to E2 with a standard inner product. Fine. Similarly, the vector 1 1 is orthogonal to 1 minus 1, the standard inner product is 0. Again, you can also have 2 comma 1 and 1 comma minus 2, their inner product is 0, standard inner product. Fine. But we had asked you, so recall that we had asked you a question in which what we wanted was find A, B, B, D such that the inner product of 2 1 with 1 3, this was 0. All right. Fine. So depending on the requirement you can try them out, but as I said, we will always be looking at a standard inner product. So don't worry, you should know how to find it out, but in the exam if I am saying something, it will be with respect to the standard inner product. Fine. So be careful. So try them out. All right. For example, now look at example, another example in R3. Then the set E1, E2, E3. If I look at this set, then one is perpendicular to the other. E1 is perpendicular to E2, E2 with respect to E3, E3 with respect to E1 and so on. Not only that, if I look at this vector 1 1 1, this is perpendicular to 1 minus 1 0. This is also perpendicular to 1 0 minus 1. Fine. Something which is perpendicular to both of them, x y z. I want x y z to be perpendicular to this as well as this. I would like you to see that this is nothing but alpha times 1 1 minus 2. All right. How do you find it out? We'll just look at it one by one. So question, suppose we need to find x y z, or in terms of column, find x y z such that x y z comma 1 1 1 this is 0, and xyz times 1 minus 1 0 is also 0, both of them are 0. So this part tells me, the first example, the first condition tells me that x plus y plus z is 0. The second condition tells me that x is equal to y. All right. So now I can solve it to see that, you can see that x is equal to y here, and once x is equal to y, z is equal to minus 2x. So this is what I get here. Fine. And there's infinite number of solutions and things like that. We'll come to that afterwards again. So I would like you to keep track of that. The next thing that I would like to understand, make you understand, is what is called the triangle inequality. So what was the triangle inequality? If you remember from your school days, triangle inequality says that if some things are sides of a triangle, all right, so if I have some sides here, if this length is a, this length is b, this length is c, then the length of a plus length of v is greater than equal to length of c. All right. So we need to talk of length of a, length of b, length of c, things like that. Fine. So in terms of our vector space, it turns out that if let V be an inner product, let V be an inner product space, then for any u v belonging to capital V, length of u plus v is less than equal to length of u plus length of v. This is what the triangle inequality is. Fine. So in some sense, what you can see is that starting from 0, so this is the 0 vector that I have, I go to u, I go to v, so this is the vector which is u plus v. Fine. Then we are saying that length of this vector is less than equal to length of this vector plus the length of this vector. That's what we are saying here. Is that okay? Or the length of the hypotenuse, the length of the diagonal is less than equal to length of the two sides. That's all we are saying here. Fine. So let's try to prove this part, which is very important. So when we are saying this, so length of u plus v, I'll look at a square of that. I don't want to look at just this. So this by definition is equal to u plus v, comma u plus v. This is equal to, by definition, is uu plus vu. All right, u with u, v with u, this is what I have done, plus u with v plus v with v. Now this is equal to, all right, in absolute value, so modulus of this, if I look at, modulus of this, if I look at, this is less than length of u. So Cauchy Schwartz inequality says that uv is less than equal to length of u into length of v. So let's use that part. This is equal to length of u square, this is equal to length of v square, and this part is less than equal to this. So plus, so this is less than equal to 2 times length of u into length of v, and therefore I get that this is u plus v whole square, and therefore I get that length of u plus v is length equal to length of u plus length of v. Is that okay? Fine. You get this part. You also have what is called, so if u is orthogonal to v, so orthogonal to v means, look at the definition, it says that u comma v is 0. Fine. In that case, this will turn out to be equal to norm of u plus v whole square will be equal to norm of u square plus vu plus uv plus norm of v square is nothing but norm of u square plus norm of v square. All right, because this part is 0 from here. Fine. So what we are saying is that if u and v are perpendicular, so I have u here, so starting with 0 I have got a u here, I have got a v here. Fine. Make this parallelogram for you. This is the hypotenuse. The length of this square is length of this square plus length of this square. All right, this is what it says. So this is what the Pythagoras theorem is. So when something is perpendicular, everything is nice. We will look at these applications in the next class. Fine. I would also like you to, as the last thing, I would like you to understand this, that in there is a notion of what is called a parallelogram law. So what is the parallelogram law? Let us try to understand it. So it says that I have the vector u here, vector v here, just join it here. This is the vector u plus v, and this is the vector. So I am going from this, suppose I am going from this direction. Fine. It means that I am going u and v here. So this vector for me is, well, I am going like this, v minus u, I am looking at this part. So let us look at the lengths here. So I want to compute what is norm of u plus v whole square plus norm of v minus u whole square. I want to compute this. Fine. So this by definition is equal to, look at this, I have already computed it for you. So it is u plus v comma u plus v. This is nothing but v minus u, v minus u. So this gives me u square plus v square plus uv plus vu. Alright, this is what it gives. What about this one? This gives us norm of v square plus norm of u square. Again minus u gives you plus u. Now it is v and vu with a minus sign, minus vu minus uv. Alright, this is what I get. So if you just look at this and this cancels out, uv with uv cancels out, vu with vu cancels out. Alright. So therefore what I get is 2 times length of u square plus length of v square. This is what the parallelogram law says. Parallelogram law says that, so the parallelogram law says that the sum of squares, the length of the sum of a square, the sum of squares of the, so I think language will be a problem. So let me write as say a, b, c, d. Then it said that look at ab square, alright, fine, this length ad square, take twice of this. This is same as ac square plus bd square. So we used to prove it using Pythagoras theorem. Same thing is happening here also. This is a very important theorem, parallelogram law. Even though the proof is very simple, the idea is very simple, but it's very, very important. I would like you to keep track of that. We will be using this idea to say something is possible, something is not possible. Is that okay? So keep track of this part, that ab square plus ad square, or look at the sides. Alright, square of this, which is nothing but u square. Similarly, a square of this, which is v square, twice of that is equal to the sum of the squares of the diagonals. Is that okay? So that's all for now. Thank you.